Welcome to video lecture number 3. Last time we talked about the significance of the groups and periods on the periodic table and established that elements in the same group or vertical column have similar chemical properties because they have the same number of valence electrons. In this video, we'll talk about metallic character, a term that describes several chemical properties all at once. The most common misconception about metallic character is that it somehow describes the physical properties of an element. When someone says, "That's metallic," you might think of something shiny and hard, or maybe even a wire that conducts electricity. But what you're thinking about are the physical properties of metals, properties that you can observe with your 5 senses. In this video, metallic character refers to a chemical property of metals, namely, their tendency to lose valence electrons in chemical reactions. It may be helpful to watch or re-watch video lecture 6 from our unit on atoms to help you understand the term better. In the second part of this video, we'll look at a few examples of how to use the periodic table to predict how atoms will form chemical bonds. To understand the term metallic character, you have to understand that atoms can be reactive for 2 reasons. Ionization energy and electronegativity are 2 big sciencey sounding words that describe something you already know. Some atoms are reactive because they want to get rid of their valence electrons, and others are reactive because they want to take valence electrons from other atoms. Before we talk about these terms, though, I want to look at the size of atoms of different elements. On the right, there's a periodic table that compares the size of atoms of each element. Atomic radius is a measure of an atom size, and if you look at the table, it's a little bit surprising. Having modeled the first 18 elements yourself, you probably think of an atom of neon over here as being much bigger than an atom of lithium over here. But that's not the case. Neon has a lot more protons and neutrons than lithium, so it is a lot heavier, but it turns out that lithium is a lot bigger. Remember that the mass of an atom, its weight, is all in the nucleus, but the nucleus is very dense and tiny. The volume of an atom or its size is purely determined by its electron cloud. Lithium and neon are both in the second period, though. They both have 2 energy levels, so why is neon so much smaller? It has to do with the electrical charge of the nucleus. Lithium only has 3 protons in its nucleus, and only 1 valence electron in the second energy level. The electrical attraction between the positive nucleus and the negative valence electron is pretty weak. So lithium's valence electron is far away. Its second energy level kind of expands outward. You can think of lithium as having a very weak grip on its outermost energy level. Neon, on the other hand, has 10 protons in its nucleus that pull its 7 valence electrons in with a greater force. Its nucleus pulls the electrons in much closer than lithium's. The greater the electrical charge, the greater the attraction, which leads to smaller atoms. That's why the size of atoms or atomic radius increases as you go from right to left. Notice that the atoms get bigger as you go down as well. Even though the nucleus of the atoms is getting heavier, these atoms in group 1A still only have 1 valence electron. But as you go down each period, you add an energy level that is further and further from the nucleus. Even though francium has a lot of protons in its nucleus, its valence electron is so far away that there isn't a lot of electrical attraction, and the atom ends up being huge, for an atom anyway. In summary, the atoms get bigger as you move down and to the left on the periodic table. All right, now that we've discussed the size of atoms, ionization energy should make a lot more sense. Don't let the term intimidate you. It sounds fancy, but it's very simple. Ionization energy is the energy that it takes to pull away a valence electron from an atom during a chemical reaction. Ionization energy is directly related to the size of an atom because the fewer valence electrons an atom has, and the further they are from the nucleus, the easier they are to pull off. So ionization energy increases as you go up and to the right. It gets easier and easier to pull electrons off of atoms the bigger they are. You can think of an atom with a low ionization energy, like francium down here, as having a loose tooth. It's easy to pull its valence electron away. Atoms up here, like fluorine, have high ionization energies. It's very difficult to take their electrons from them because of the strong electrical attraction between their nucleus and their valence electrons. So ionization energy once again increases. It gets harder and harder to pull electrons away from elements when you go up and to the right. Electronegativity describes how much pulling power an atom has on another atom's valence electrons. The smaller an atom is, the closer its nucleus can get to other atoms' valence electrons to pull them away. So electronegativity is also related to the size of an atom, and it's sort of like the opposite of ionization energy. Francium has a low ionization energy and a low electronegativity. It's easy to pull electrons away from francium. And francium, because its electron cloud is so big and nucleus is so far away from other atoms, isn't going to be taking electrons away from those atoms anytime soon. Its nucleus is at the center of a huge electron cloud. Fluorine, on the other hand, has a high electronegativity and a high ionization energy. Its nucleus has a firm hold on its own valence electrons, and electronegativity says it would happily pull other atoms' valence electrons into its own outer shell to satisfy the octet rule. Like ionization energy, electronegativity increases as you move up and to the right on the periodic table. Together, ionization energy and electronegativity determine the metallic character of an element. Again, we're not talking about how shiny the element is. We're talking about a type of reactivity. So metallic character is related to valence electrons and how easily an element loses them. Because metals are in this general area of the periodic table down and to the left, they tend to be bigger atoms that have low ionization energies or easily lose valence electrons, and they have low electronegativity. They don't pull on the valence electrons of other atoms with very much force. So when we describe an element's metallic character, what we're really talking about is how likely that element is to lose its valence electrons in a chemical reaction. The greater an element's metallic character, the more likely it will lose electrons and become the positive ion in an ionic bond. The metallic character of elements increases as you go to the left and down the periodic table. Thanks for watching.